I'll talk briefly about the work I carried out during my thesis entitled Modeling Techniques to Inform the Design of Sub-Wavelength Periodic Acoustic Structures with Henry Rice in Trinity. So I'll just go briefly behind the motivation behind this research work. So as we all know, the impact of environmental noise on health has been extensively researched. It's linked to the development of cardiovascular related diseases and increased levels of stress. Aircraft noise is one of the most damaging impacts of aircraft noise is one of the most damaging impacts of aviation noise. And with ever increasing passenger numbers, actions must be taken to reduce noise emissions within this sector. So the EU set out a target reduction of 65% of noise emissions by 2050. And these rules were set out, are derived from the ICAO strategy, which relies on 4 pillars. So sustainable management of land around airports, introducing noise restrictions and reducing noise levels at source, which is the area we'll focus on. So the turbofan engine is the largest noise contributor in that regard, and currently sound attenuation is primarily achieved through acoustic liners within the nacelle. And the space and weight allocated for noise treatment within the nacelle is quite restrictive. As such, there is a potential for acoustic metamaterials to become a better suited alternative to liners for noise mitigation. And this avenue has been aided by the advancement in additive manufacturing. So as such, the focus of this work will reside on reduction of noise propagating outside turbofan nacelles and explore the potential of metamaterials to reduce civil aviation noise. So as part of this, the Aerialist project, which stands for Advanced Aircraft Noise Alleviation Devices Using Metamaterials, which partly funded this work. It's a project which was centered around 3 core work packages, which was divided between different partner institutions and coordinated by Romatré. So the numerical prediction, Romatré and the University of Bath focus mainly on propagation tools, while KTH focus on solid mechanics of metamaterials and structural modeling of the anisotropy and some characterization. And in Trinity, we focused on practical modeling tools for benchmark simulations, as well as design and manufacturing, and the core of all the experimental validations were carried out in Bristol. So what we currently have in terms of noise treatments are acoustic liners. They're based on simple 1 degree of freedom Helmholtz resonator, which consists of a outer perforated sheet backed by a honeycomb cavity and impervious layers. And this has been extended to 2 modes with 2 layers in series. Through additive manufacturing, we can scale up the complexity from 1 or 2 degree of freedom to n degree of freedom. And as part of this, we examine different types of metamaterials. So some simple just array of resonator, either tuned at particular frequencies, and as well some partners focus more on providing vibrational bandgap. However, the focus of my work focused on airborne absorption. So the primary aim of the thesis was to develop an efficient design tool which predicts induced losses in 3D printed sub-wavelength acoustic structures. As part of this, several objectives were set out. So numerical modeling of a benchmark metamaterial design, along with experimental validation using different additive technologies. And in a second stage, we looked at combining analytical and numerical tools to obtain a more efficient design tool process. So as part of this, there was 2 different studies realized, one which used these detailed viscothermal modeling description via FEM of the unit cell, and then a transfer matrix method to obtain the performance from a built-up structure, and another one which uses just reduced order modeling to approximate viscothermal losses within the cells. And finally, there was some sensitivity analysis carried out and a parametric study on a set of multi-layered perforated panel configurations. So the approach used to assess the performance of the design is presented here. As part of the periodic acoustic structure that is designed, there's a representative unit cell. On one hand, you try to numerically predict the acoustic behavior in microacoustic systems. We know that there are important dissipative effects that need to be included. So this detailed description is required when you to analyze such behavior. And on the other side, the designs can be produced swiftly due to the advancements in additive manufacturing, and the acoustic behavior of the structure can just be characterized under normal incidence. So it allows to validate the current design and then inform potential design modifications. So the numerical study, which is presented here, proposes on a benchmark design, which was proposed by Thomas Zielinski in the DNORMS cost action. So this acoustic metamaterial design is easily reproduced, and it's amenable to rapid prototyping techniques. And through the repeatability of the unit cells, you can build up structures can easily be reproduced. And it's a structure that is well suited and can be well suited and easily reproduced through additive manufacturing. And it also allowed to assess different manufacturing techniques. So the acoustic performance of the structure it was also part of a round-robin study which members of the LUM here were also part of. So it leads to interesting built-up structures based on the fundamental cell can also be reproduced through space calling and labyrinthine structures to obtain a more desired acoustic response. So here we have just a small overview of the design process, and a part of this study, 4 different printing technologies were used to manufacture these so-called DNORMS samples. So each resultant print has inherent defects that is characteristic of the manufacturing employed. So FDM has remaining spurs, usually in the voids. And with DLP technology, you're using an LCD screen with a UV backlight. So there's a sort of staircase effects due to the pixels. And then SLM and SLA both showed the highest fidelity to the produced part, and they both use focused lasers. So on the modeling side, so the main of the modeling was done through console. So with viscothermal formulation was applied to the periodic cells, and then a simple waveguide with just a Helmholtz formulation was put at the inlet, mainly for boundary condition and to allow a plane wave and full absorption of the reflected wave. So with such design, you need a careful meshing strategy that needs to be employed, because there's important losses within the boundary layer that need to be taken into account. The results obtained here are presented for depth of 10 cells. So the numerical model usually underestimates the losses in the system, because you're representing an idealized version, and depending on your printing technology employed, you have a part, more or less about a 0.15 amplitude difference between the absorption obtained through different technologies and your one predicted. And SLM and SLA provide closer match to predicted results, whereas the resultant acoustic behavior obtained from the FDM and DLP is further off due to increased roughness and microporosity, but for SLM you still have like a lot of microporosity. So then you can have just through basically combining different lengths together, you broaden your absorptive peak. So the space calling design was inspired just by the influence of the layer depth on the frequency response. So you can see just the thermal and viscous boundary layer profile at 500 Hertz for different combined lengths. And the graph just shows the results obtained for different depths and the corresponding experimental measurements obtained under normal incidence for SLA prints. So the design was realized through 4 different additive manufacturing technology, which range from low-cost machines to state-of-the-art printer, and the matches are quite reasonable between the two, considering the differences in technology employed. So then, I mean, you can use, in order to realize low-cost design tools, for metal material, it's necessary to avoid expensive full viscothermal formulation. So there was just a small, simple reduced frequency model based on a wide duct. Even though it's usually restricted to non-varying cross-section, where it still works quite well. Just on this graph compared to the previous slide, the bulk viscosity isn't 0, it's just taken at 2/3 of beta. So that's why you have a slight difference with the previous one. And so the results presented here are also on a configuration of 10 depths. So as part of this, there was just 4 different technologies evaluated against numerical results, and there was good agreements produced both against other work from the given by the cost action, and just it enabled basically to assess different printing technologies against each other and to see that, I mean, there are deviations and they're either dependent on geometric tolerances, surface roughness, but it's they provide quite a reasonable match with the rest. So then, so even though additive manufacturing has many advantages, using more simple traditional subtractive method, it's possible to obtain structures which show promising absorptive behavior. So just simply by using tortuosity within the design, you manage to lower the first resonant frequency. So, and then you can just use simple modeling on one step and then just propagate that using just transfer matrix method. So that's what was done here. So 2 simulations were carried out to obtain the necessary pressure and velocity variables then to be used in transfer matrix. Results were obtained for just 5 multi-layered units, and the experimental measurements obtained are compared with results with and without a manifold. So mind you, in this, there should have been some an added end correction as well. And there's different vibroacoustic effects that aren't really represented numerically. So the design presented multiple high absorption peaks with sub-wavelength behavior. The transfer matrix approach is both efficient as it gives a fast estimation about the acoustic behavior of the built-up system. And the design presented makes good use of the available cavity space through tortuosity. So the shift in frequency between porosity correction and then just using a sort of manifold for having a fully developed plane wave can explain some differences in the system. But despite these small errors, you still have like the Gaussian shape of the experimental curves, which are well reproduced, and you have a comparison of a lossless acoustic model that can confirm the frequency range that's due to the thermal and viscous losses, sorry. And then just as an extension of that for further plates, since calculating viscous and thermal interactions in porous media is quite difficult, description of viscous and thermal effects have been provided first by Kirchhoff and then extensions to this by Zwicker and Kosten and Stinson. The theory provided here is just a description based for a small cylindrical tube for your viscous and thermal effects. It vanishes at the wall, and you've got your temperature being 0 at the wall. So from this, you can then use get your density and your bulk modulus. Then for those sort of plate design, the focus was on the dissipative effect within the slit, within the air gaps of those plates. So first, we investigated just on a stack of 8 cells. So it ranges from 32 millimeters to 56. So you get, I mean, quite low absorption at 600 hertz. And then from this, we just selected what optimal air gap we should use for experiments. From this, it should have been 2, but then from the different manufacturing constraints we had, in the end, we selected 1.5. And then we just used this, the model from Allard to describe the losses within the slits. So in this sort of design, the parameters that were deemed to be important were the hole radius, the air gap spacing, your plate thickness, and the hole location. So those are just results which show the difference between numerical and experimental. You've got some vibroacoustic coupling as well, which wasn't reproduced. You observe the same magnitude difference between using a reduced order model, viscothermal model, and allowing for some sort of print correction between your layer heights. So there was a print correction put on of 0.25 on the pores. And with FDM printing, usually your holes are slightly undersized. So the main aim was just to take like a very simple sort of model and then applying partitions in between. So you're decoupling resonators and you're having them acting in parallel. So from this very simplistic design, then you can aim to do some proper optimization and get more complex structure, and you're increasing the bandwidth. So it was, at first, it was just without any sort of partitions, then with partitions, and then 2 differing hole sizes, and then using with 4. Yeah, there's just one with 2 different hole size shows and sorry. But mainly for validating numerical models, since they were just using acoustic model, I just did different acoustic structure models were made, and incorporating the structure didn't lead to any dramatic changes, just by using microscopy images to see exactly what was going on, but then even taking these same plates in different sets of configuration. So all these plates, A, C, all A's are the same, all C's are the same, combining different ones, you get slightly different results. And as well, when you're setting up your experiment, you're not tightening them exactly the same, so you don't really know exactly what occurs in between the plates. But you can see that the first resonant frequency is quite well represented. So then, since couldn't do more experiments at that stage, the rationale behind this was more to impose in between the plates a sort of a leakage which corresponded to a layer height between the plates to see was there some sort of disconnection. And and phase opposition. So it was mainly to rule out the existence of an acoustic mode at 2500. And so the plates were printed as two separate components stacked together. And so there was just one trial done with using a spring, but the displacements that would occur would be quite small. So that's why the rationale behind imposing a leakage, which corresponded to the layer height of material. And then from this, just using a free vibration studies to see that the resonance shown was around at 3,500 hertz, which is quite high, but it's difficult to correct without applying proper boundary conditions, but more experiments are needed, either to use the usage of a vibrometer to exactly account for this. But it still exhibited high absorptive peaks at low frequencies, and the change of either change of manufacturing strategy to remove those existing structural resonance, or even exploiting this vibroacoustic coupling, because you get an added dissipative effect. But all in all, just this simple design of just decoupling resonators, it increases your broadband absorption. So you have them acting in parallel, and it's quite a simplistic task. So just conclusions of most of the work that was on, it was just to have a sort of rapid developmental design process, and it can be aided by efficient modeling tools and to obtain sub-wavelength absorptive structures. The usage of printed metal materials evaluated as noise-reducing treatment. There's an added uncertainty that arises from printing, which is not necessarily bad, but predicting it, you have to be quite tolerant with what you get. Then there's those quite promising multi-layered plate concepts for noise reduction, just using resonators and basically acting in parallel, and through the use of reduced order modeling that are comparable to what you get from a viscothermal formulation, are more efficient at the design stage. And you have a good route between just using a transfer matrix approach with a unit cell modeling, and it's quite good from a design aspect. Then some additional work which was carried out in a preliminary stage, just under shearing flow. So thanks, and I'll just go briefly just some of the publications associated with the work. Then just small, just to see if there was any use of using homogenization for these sort of plates, but they're quite big structures, so in my view, it's probably a bit too simplistic from that sense. And then just work that was done with Eve and Thomas to try and see those plate configuration under shearing flow, and the design themselves, even those sort of labyrinthine structures, they're quite stable, just at different sound pressure level. It's still quite linear, and then under flow, it's performs still quite well. So, and then just other experimental work on just phase gradient absorption device. Thank you.